Hello everyone, I am a student of IIPS JVV Indore. My name is Aditi Trivedi and today we are going to learn some important questions of TOC, Theory of Computation. So our first question is, use the set of production to show that each of these sentences is a valid sentence. Number 1, the happy hare runs. So the sentence, the noun phrase, intransitive verb phrase, the article adjective noun intransitive verb phrase, article adjective noun intransitive verb, the happy hare runs is a valid sentence. And then the next is the sleepy tortoise runs quickly. A noun phrase intransitive verb phrase, article adjective noun intransitive verb phrase. Our third point is the tortoise passes the hare. Noun phrase in transitive verb phrase, noun phrase. So it is a valid sentence. The sleepy hare passes the happy tortoise. Noun phrase, transitive verb phrase, noun phrase. So we will see the evaluation of postfix expression. Given a postfix expression, the task is to evaluate the postfix expression. Postfix expression. The expression of the form AB operator AB plus, that is, when a pair of operands is followed by an operator. Example, input str 231 cross plus 9 minus, output minus 4. Explanation. If the expression is converted into an infix expression, it will be 2 plus bracket 3 cross 1 minus 9 is equals to minus 4. Input string 100 to 100 plus 2 divided by 5 cross 7 plus, and the output is 757. Our next question is construct derivation trees for the sentences in Q. The happy hare runs. Sentence, noun phrase, intransitive verb phrase. Article, adjective noun, intransitive verb. A. The happy hare runs. The sleepy tortoise runs quickly. The tortoise passes the hare. Sentence, noun phrase, verb phrase. Article, noun, verb. The tortoise passes noun phrase. Article, noun. Article is the noun hare. The sleepy hare passes the happy tortoise. Sentence, noun, phrase, verb phrase. Noun, article, phrase, adjective, noun, verb phrase. The sleepy hare passes noun phrase. Article the, and the noun is tortoise. Usage of NBNF with signed decimal numbers. EBNF, extended Backus NOR form, is a widely used notation for describing the syntax of programming languages and other formal languages. It allows us to define the structure and rules of a language using a set of production rules. Here is an example of using EBNF to define a grammar for signed decimal numbers. It is given below. In this grammar, a signed decimal number consists of an optional sign followed by one or more digits. The sign can be either plus or minus. The digit can be any of the decimal number from 0 to 9. Our third question is, construct a phrase structure grammar that generates all signed decimal numbers consisting of a sign either plus or minus, a non-negative integer, and a decimal fraction that is either the empty string or a decimal point followed by a positive integer where initial zeros in an integer are allowed. As sign integer, positive integer, sign plus, sign minus, integer is equals to digit, integer digits are 1 2 3 4 5 6 7 8 9 up to 0. Sentence, noun phrase, intransitive verb, noun phrase. Article, noun, article is the noun tortoise. Intransitive verb passes, and the article is the noun hare. Positive integer, non-zero digit, positive integer, non-zero digit integer. The sleepy the sleepy tortoise runs quickly. Sentence, the noun phrase, intransitive verb, the article is the adjective sleepy, noun tortoise. Here also intransitive verb runs, adverb quickly. Extended Backus nor form. Extended Backus nor form is a notation used to describe the syntax of programming languages and formal grammars. It extends the original Backus nor form notation with the additional features for expressing complex grammatical structures. Okay, explanation of examples. The first example defines an expression as either a term or a term followed by a plus sign and another sign. B. Give the Backus NOR form of the grammar. Sign decimal number, sign integer, positive integer, sign plus or minus, integer digit or integer digit, digit 0 up to 9, non-zero digits 1 up to 9. Positive integer, integer which contains non-zero digit. Non-zero digit contains integer. Non-zero integer contains non-zero integer or zero integer. Signed integer में integer, signed digit is equals to 0, integer 9 digit 9. Give production rules in Backus NOR form for an identifier if it can consist of one or more lowercase, at least 3, but no more than 6 lowercase letters, 1 to 6 uppercase or lowercase letters beginning with an uppercase letter, a lowercase letter followed by a digit or an underscore followed by 3 or 4 alphanumeric characters. One or more lowercase letters, identifier L letters, identifier letter A, B, C up to Z, at least 3 but no more than 6 lowercase. A, B, C, either you can see identifier L letter, L, C letter, 1 to 6 uppercase or lowercase letters beginning with an uppercase. Uppercase A, B, C up to Z. D. A lowercase letter followed by a digit or an underscore followed by 3 or 4 alphanumeric characters. Here we can see the lowercase ABC up to Z, uppercase ABC up to Z, digit 0 to 9. Give production rule in Backus normal NOR form that generates all identifiers in the C programming language. It can identifier starts with a letter or an underscore that is followed by one or more lowercase letters, uppercase letters, underscores and digits. Here numeral sign non-digit decimal sign 0 decimal sign plus or minus non-zero digit 1 up to 9 digit 0 which is a non-zero digit decimal digit cross. Give production rules in extended Backus NOR form for identifiers in the C programming language. Identifier letters symbol letters L letter symbol letters digit letter LC letter UC letter lowercase and uppercase. Lowercase is all the small characters small and uppercase all the capital letter characters and digits are 0 up to 9. Then we can see usage of EBNF with the C identifier. Syntax and rules. EBNF extended Backus NOR form is a notation used to describe the syntax of programming languages. It is basically used to describe the programming language's syntax. It consists of a set of production rules that define the structure of valid statements. Rules for C identifiers must start with a letter or an underscore. They can be followed by any combination of letters, digits and underscores. Here some examples are also given. Then we can move to our next slide. For each of these strings, determine whether it is generated by the grammar given for postfix notation. If it is, find the steps used to generate the string. Okay, so first is expression A, term, adopter, factor, multiple operator, add operator, identifier, multiple operator, add operator. Here, same as A, C or D, we can also find this. B, and we can see that B is not generated here. Use Backus NOR form to describe the syntax of expressions in infix notation. So here we can see that point A and D is not generated. Okay, so we will see about B and D. B and C. B expression term, add operator term, factor, multiple operator factor, add operator, फिर factor, multiple operator factor. Identifier, which is A, multiple operator, identifier, then add operator, identifier, then it is multiple operator and identifier. Same as this, we can solve also other expressions like m cross n plus p and m plus n cross p minus q. Construct a finite automata PTA Turing machine to accept the set L of all the strings over 0 to 1 ending with 101. To construct a finite automata for the language L of all the strings over 0 and 1 ending with 010, we can use a basic idea of a DFA, where the machine transitions to an accepting state when it reads the specific sequence 010 at the end of the input string. Here the formal construction states are Q0, Q1, Q2 and Q3. Q0, Q1, Q2 and Q3. Alphabets 0 and 1. Start state is Q0 and acceptance state is Q3. So here we can see Q0 is a self loop which contains 0 and 1, and if Q0 is going to Q1, then 1, and then we can see Q3 is the initial state. So here Q2 is going to Q4 with the value 1 and Q1 is going to Q4 with the binary value 0. For a pushdown automata, the concept is similar, but we can use the stack to keep track of the last 3 symbols, read and accept if the sequence is 010. However, this requires a more complex PDA design. For a Turing machine, we can design it to scan the input tape from left to right, maintain the last 3 symbols, read on its tape, and accept if the sequence 010 is found at the end of the input string. This also requires a more elaborate design. A PDA is defined as given in this. So R1 contains delta Q00Z0, Q010, Q011Z, Q010Z, Q000, Q01. So here uh, we can see that by rule 1 we can generate this, and by rule 4 we can generate this, and by rule 7 we can generate this. So our PDA is constructed as we can see here. Our next question is concept of TM Turing machine to accept the set L of all the strings over 0 and 1 ending with 101. As we can see that in a Turing machine we can design it to scan the input tape from left to right. So here by using this approach we can see this diagram and explain this. To construct a Turing machine that accepts the language 0 cross 1 and plus 1 cross 0, where 0 cross represents 0 or more occurrences of 0 and represents concatenation, we can design a Turing machine that reads the input string from left to right and check if it matches either patterns. Here the high level description of Turing machine. Start in the initial state Q0 and move right along the tape until the first one is encountered. Okay, and the second step is if one is encountered, move to state Q1 to process the rest of the string. In state Q1 continue moving right until a 0 is encountered. अगर हमें 0 encounter हो जाता है, move to the state Q2 to process the rest of the string. In state Q2 continue moving right until the end of the string. If the end of the string is reached, except if any other symbol is encountered, reject. Here the formal description of Turing machine is given Q0, 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 Q1, Q2, Q3, Q4, Q5 and Q6. Here we can say that a self loop contains BBR and When it encounters 0xr, it goes to Q1, and by looking all this, we can mm, make this diagram. Construct a PDA equivalent to the following CFG. To construct a pushdown automata equivalent to the given context-free grammar, we can follow these steps. The PDA stack alphabet will include the symbol, and the input alphabet includes and the marker symbol indicating the bottom of the stack. The PD states will include the start state Q0, the accept state Q, and several other states to handle different parts of derivation. The PDA transition will mimic the rules of the CFG. From Q0, if the input is 0, push B onto the stack and transition to the state Q1. From Q1, if the input is 1, push S onto the stack and transition to state Q2. From Q2, if the input is 0, push S onto the stack and transition to state Q3. From Q3, if the input is 0, push S onto the stack and transition back to the state Q2 to handle the second S in OBB. Finally, the PDA should accept if the state is empty and the input is consumed. To test whether the string is in the language generated by the PDA pushdown automata, we can stimulate the pushdown automata on this input. Start in state Q0 with the input and the stack initially containing following the transitions of the PDA based on the input symbols and the stack contents. If the PDA reaches the accept state with an empty stack after processing the entire input, the string is accepted, otherwise it is rejected. In this case, the pushdown automata will reject the string 0104 because after reading 010, the PDA will be unable to consume the 4 since there is no transition defined for Q2, 4 and S. So we are concluding it, and some key points are: formal languages and grammars are used to describe the structure and rules of the language. English grammar is a subset of formal languages and can be described using grammars and rules. Postfix notation grammar is a mathematical notation that represents operations using a stack. Extended Backus nor form (EBNF) is a notation used to describe the syntax of programming languages. Examples and derivations help illustrate the application of formal languages and grammars. Thank you.